Good day, Math 30-1s. Today we are starting a brand new unit, this one called Trigonometric Identities. And what we're starting to look at is an extension back to Chapter 4 and the unit circle, and building another layer on top of that. We're really going to look at being able to connect sines, coses, tans, and really relate them all together using something called an identity. So we'll get into that in just a moment, but what we are talking about today is looking at complex statements and trying to make them simpler. So I could look at a statement like cos times tan and say, is there any way to make that look simpler? Another way might be saying, could it be sine of x? Could I make this look like sine of x? And some of you might say, well, I know that tan of x is sine over cos, which kind of tells you that maybe some coses could cancel. So in a way, this is sort of the same thing. Sine is sine. So is the following statement true? I would say sure. Always? Well, the only risk in saying that they are always true is that there is a denominator, cos of x. And if you have a denominator that can be a 0, we might say that that's not allowed. So the only risk when we say always is that as long as cos of x is not a 0, and on the unit circle, cosine is 0 at 90 degrees and 270, as long as our angle isn't 90 or 270, I'd say, yeah, it's true. This brings us into a conversation about non-permissible values, which we've heard before. And non-permissible values are also known under another name, restrictions. So we are restricting angles if they are in a denominator position. As a side note, a reminder that when we're talking about a divided by b and a bigger division of c over d, there's more than one denominator position. If this b were 0, a divided by 0, the top fraction would become undefined and the whole thing becomes undefined. The bottom fraction, if d was a 0, the bottom fraction has a c divided by 0, and the bottom doesn't exist, so the whole thing doesn't exist. But in fact, if c was a 0, then you have 0 divided by something, which makes this giant denominator 0, and then whatever was on the top is dividing by a giant 0, and again it's undefined. So b, c, and d are technically both denominator positions, which we could say are not allowed to be 0. So those are important locations. Now as we talk about dividing fractions by fractions, I should mention that there is a traditional way to divide fractions by fractions. If I were to say a divided by b, and then dividing by c over d like we just saw a moment ago, the traditional way of saying a over b divided by c over d is to write the second fraction reciprocated as you change the operation to a multiply. Now there is simply just a connection between your numerator and denominator that creates AD over BC. This is a more clean way of writing that giant fraction divided by a fraction. Now I do want to share a little bit of a strategy that I sometimes use, which can help but isn't maybe crucial. What I like to do is I like to take the two denominators, the b and the d, and I like to think of shifting the b down a level and the d down a level, which technically goes up to the top. What you end up with is an a with a d and a b with a c. In fact, that is the same as we had a moment ago. Maybe a bit of a trick. Now it is with a bit of caution that if you wanted to try this, it can be nice, but it is a little bit risky in that it's a shortcut. So if I were to say what's a more concise way of writing 2/3 divided by 5/7, I might say the 3 could come down a level, the 7 goes up to the top, the 2 connects with the 7, and the 3 moves down with the 5. You might look at this and say 14 over 15 is the answer, which it is. Maybe that's a bit more quick. Again, one of the inherent risks in learning shortcuts is that there are special cases. Now I do have to mention that there's no denominator underneath this 3, so I might say the only denominator is the 2. So I could more cleanly say this is 1 divided by 2 times 3. If you take half of a cup of flour and you divide it into 3, you end up with a sixth 3 times. And the other possible scenario, there's only 3 other scenarios this could look like, is what if you say 5 divided by 4/3? Only denominator is the 3, which comes up a level, and we'd have a 15 over 4. So there are some risks in this, but this is going to be a strategy that I'm going to employ today to make things perhaps a little bit more quickly. Otherwise, if you don't like that, you get to revert back to reciprocating and changing the division to multiplication. So what we're going to talk about today is a continued non-permissible value discussion. What are the non-permissible values for tan of theta in the domain of 0 to 2 pi? We already learned what the tan graph looks like, and it had these asymptotes at certain places, but we're going to avoid thinking about these asymptotes for a moment and just think about denominators. Now tan of theta is sine theta over cos of theta, but there is a denominator position, cos of theta, which is not allowed to be 0. So we're going to think about the unit circle and say, when is cosine 0? That's not allowed. And the answer is at 90 and 270. So we could say that at 90 and 270, we have restrictions. So I can say that theta is not allowed to be those 2 values, because if it were, it would make the bottom of your fraction 0. Now this happens in many occasions. When we start talking about cosecant, we're talking about 1 over sine of theta, which is dividing by a cotangent, which isn't sine over cos, but cos over sine. Referring back to which of these is in a denominator position, sine can't be 0, cos can't be 0, sine can't be 0. So we ask on the unit circle where sine is 0, where cos is 0, and in fact at all 3 spots, excluding, because of the round bracket, excluding 2 pi, we can say when theta is 0, pi over 2, pi, 3 pi over 2, and I don't get to say 2 pi because it's got a round bracket, but we get to say theta is not allowed to be these angles, because if it were, it would create zeros in a denominator position. Questions can get a little bit more complicated, like sine of theta divided by a denominator of 1 minus cos squared. Now we could really just make this denominator equal to 0 and say, when does that happen? We could add the cos squared over to the right side. We could square root both sides to say positive or negative 1 is cos of theta, and ask, when is cosine positive 1, negative 1, and for the domain of all real numbers, we have to answer as a general solution that theta is not allowed to be these 2 arms. We're talking about not a solution to an equation, but a restriction as an equation. So theta is not allowed to be 0, 180, 360, 540, 720, and every multiple of 180. This is your restriction on theta. For letter D, it's a little bit weird to see sine minus cos, but if we again say, when is the denominator 0, and maybe add the cos over to the right side, I can ask, when is sine equal to cos? Think about the unit circle. When are your y values equal to your x values? At 45 degrees and at 225. So we can say that our angle is not allowed to be, I'll do this one in radians, 45 degrees and every 180 degree multiple. So n a pi n, where n is an integer. And this is, again, is a restriction, not a solution. So restrictions are a little bit unique. In our conversation today, we build on that idea as we talk about something called an identity. A trigonometric identity is really just an equation that is always true. We've actually seen an identity in the past, and I'm going to give you an example of an identity you've seen before. If I were to say A and B and C in this right triangle, I could give you the equation a squared plus b squared equals c squared. Pythagoras is something that you accept as fact. This works for all 90-degree triangles. There's no special cases. It just works. So the Pythagorean theorem is an example of identity comparing sides in a right triangle. When we talk about trigonometric identities, we're talking about equations as identities that are always true. Let's actually consider x being cos, y being sine. As a part of our unit circle, we defined a radius of 1, x being your horizontal, y being your vertical, and we talked about from theta adjacent over hypotenuse, cosine is adjacent over hypotenuse. Cosine is x. Sine is your opposite over your hypotenuse. Sine is y over 1. So if I say that x is always cos and sine is always y when we're dealing with trig, I can say that in this Pythagoras, x squared plus y squared is 1 squared. And what we have is our very, very first Pythagorean identity. Plug in 30 degrees, it will equal 1. Plug in 45, plug in 60, plug in 90, plug in any angle, and 1 will come out. And this we accept as fact. Now this is not the only Pythagorean identity. What we can actually do is divide everything by a sine squared. And if you take cos squared divided by sine squared, take sine squared, divide by sine squared, take 1, divided by sine squared. So I'm dividing both sides of the equation by sine squared, and what I am left with is a cos divided by sine, a cotangent, that's squared, a 1, and a cosecant squared. This is your second Pythagorean identity that we need to start saying looks familiar. Anytime that you've got 1s and sine squareds, or 1s and cosecant squareds, and cotan squareds, and cos squareds, we kind of think, well, maybe that's a Pythagorean identity. And at the very, very bottom, what if we were to take the original again and divide everything by cos squared? So cos squared plus a sine squared equals 1. Divide everything by a cos squared, and what do we get? 1, a tan squared, and a secant squared. Your third Pythagorean identity. All three of these formulas are on your formula sheet, and they are something that we now can accept as fact. We are going to be using these in the future to be turning sines into coses and things like that. So in the future, and I'll say in lesson 6.4, we're eventually going to be asked questions like this, where there's cos squareds and sines, and there's no real great way to move this over and factor it because we're dealing with sines and coses. But there is a way to convert a sine into a cos using these Pythagorean identities. So at this point, we have a way that relates sines and coses, cotans and cosecants, secants and tangents together, and we can turn our trig ratios into a new form. Now, there are a few verbs that we can talk about today. The first verb is verify, and verify is an inductive way of logic, which means let's just check one case to see if it's true. Verify means let's plug in 45 degrees as an example and see if both sides match. We could say that sine of 45 degrees, sine squared, so sine of 45 degrees, that's squared, plus a 4 should equal a 5 minus a cos of 45 degrees, again squared. So sine squared plus 4 is 5 minus cos squared. Good. So sine of 45 degrees is 1 divided by the square root of 2. If you square that, you get a half. If you take 1 over root 2 and square it, you get a 1/2. We end up with 4.5, we'll say 4.5, equals 5 minus a half is 4.5, which is in fact true. So would I say that this statement is true for 45 degrees? Yeah, you bet. So 45 degrees worked. Is there a way to see if all angles work? What if 45 degrees is just somehow special? There is a way to talk deductively about using facts to ensure everything works. So we could actually take this and somehow rearrange it a little bit and say, what if I move that cos squared over to the right side? So I can say sine squared plus cos squared equals, move the 4 over, so it's a 5 minus a 4 is a 1. And in fact, what we're left with is a statement that says every angle will work in this equation. So every angle will work in this equation. And there's a powerful statement because we are accepting Pythagoras and this Pythagorean identity as fact. Now, if we're checking graphically, I won't go through this specifically, but what you can do is you can type into your calculator sine squared theta plus 4 as one side, and you can say the right side is a 5 minus cos squared of theta, and what you should see is this equation looking exactly the same as this equation, which means they are the same. And there is a way to check this graphically if you're a little unsure. Lastly, we're going to talk about a new verb, simplify. And simplify means don't plug in a number. Can you make it more tidy? So tidy it up. Now, some of these look kind of complex, and you might start where you feel more comfortable, like with the secant over tan, which you could say is 1 over cos divided by sine over cos. Your comfort with dividing fractions is going to be of a lot of importance here. Now, what you can do is with this 1 minus tan squared, I'm going to say we can start to use these Pythagorean identities to help us out. And this is where trig identities start to feel a little stressful for some. If I were to try to make 1 minus sine squared show up in here, I would have to move the sine squared to the right side. So I could say cos squared is 1 minus sine squared. So when I see 1 minus sine squared on the page, I can swap it out with cos squared. So I could now say cos squared over cotangent squared. At this point, we've got a fraction with that little trick that I showed us at the beginning of today's lesson, where I could now say cos x moves up to the top with the 1, and you're now dividing by a sine of x times a cos of x. And in fact, those cos x's would cancel. Very, very convenient. So we're left with a 1 over a sine of x. For this one, we do have a cos squared on the top, and I'm going to actually take this cotangent, turn it into not a sine over cos, but a cos over a sine. Again, using the trick to take this bottom denominator, move it up to the top, I can say sine squared, hanging out with that cos squared, and this cos of x stays in its position, but cancels, at the same time as a sine squared over a sine gets to cancel. Sine times sine, one of those gets to cancel, and ultimately you're left with a sine of x. This whole thing really is just sine of x. Your comfort in dividing fractions is going to be what's crucial, and this is not a grade 12 skill, this is a junior high and before skill. So if you need, feel free to write these out and reciprocate the second fraction, changing your operation to a product. And our last question here, you start to take wild guesses of what you might do, and I might turn secants into sines and coses, and same with tangents and cotangents, only so that I can see sines and coses to maybe better cancel. So tangent and a cotangent, and this is what we're left with. We want to have a little bit of foresight as we work through some of these, but it doesn't always happen just yet, but eventually we will. Now right now we're not really able to cancel out a cos and a cos because there's too much going on. We can't reciprocate this bottom part because it's not one fraction, it's 2. So it's not quite our reciprocating or moving a denominator trick just yet. What we can do is get a common denominator on the bottom. I see a cos and I see a sine. Two very different statements, two very different expressions. So I'm going to put a cos over a cos to make our denominator say sine cos. Over here, I'm going to put a sine and a sine to make this denominator say sine cos. we have a common denominator. So I'm going to rewrite 1 over cos of x is now dividing by a sine squared plus a cos squared divided by a sine x cos of x. You might have just noticed something. I said sine squared plus cos squared. Said that before. What is sine squared plus cos squared? Wait for it. 1. I can actually replace sine squared plus cos squared with a 1. That is a 1. I can move this denominator up to the top and say sine x cos x divided by cos of x. Coses cancel, and in fact this giant statement is sine of x. That equals that. In the future, in lesson 6.3, I get to put an equal sign between this and say, show me that they match. Telling you that they match. And your job is to show me that they both match. So there is a bigger skill coming, and questions just get a little bit bigger, but your comfort dividing fractions, your comfort getting common denominators, your comfort factoring and rationalizing is what is going to make you successful in Chapter 6. Get a little bit of practice with your Pythagorean identities. Get a little bit of practice with the difference between simplifying, verifying, and a little bit of practice with your non-permissible values or your restrictions. And that is where we end lesson 6.1. Good luck.